Good afternoon, everyone. My name is Rez Mani, and I work for the company Allied Scientific Pro. The title of today's webinar is Laser Cleaning Method and Case Studies. I've given this webinar a number of times, and every time I try to include new activities of the company, if we developed a new system or if we did a new case study, I will add to the presentation. The webinar is being recorded, and the recording will be sent to you within few days. Also, I would like to mention that the GoToMeeting platform is not really meant for broadcasting videos. So for this reason, when I show some videos, YouTube videos, you may find that the sound does not have a great quality, but I will send you the links to all the YouTube videos. When you receive the recording, you will also get the links to all the YouTube videos. Also, I would like to say that the webinar has an educational nature as well. We talk about some principles of laser cleaning, and then we also talk about our particular case studies. So without further ado, let's go into the outline of the talk. So there's a long list here. We may not be able to cover everything, but we will do as much as we can. So I'll introduce the laser ablation process, which is a more general method, and laser cleaning would be a subset of laser ablation. There are maybe many different subsets like laser drilling, scribing, cutting, and laser ablation is only one of those. Then we look at some types of lasers used in laser ablation, and we show a video of laser cleaning and compare them with the other competing surface cleaning methods. We go into the physics of laser cleaning and talk about the dependence of laser ablation on material properties and laser parameters. We explore different time zones, femto, pico, and nanosecond regimes. We compare galvo and polygon scanners. And then we talk about some applications of laser cleaning, aviation and nuclear industries. So wherever I talk about application, this means that this application exists. We haven't done them, but you know, we just like giving you the knowledge that this exists. And whenever we talk about case studies, the ones that we did ourselves. We also introduced our various laser systems of different wattages, and there's several case studies. And at the end, again, we go to some more applications, the laser cleaning in food industry and in laser cleaning of bacteria infected surfaces, which comes from some research I've done and some paper I've read. So I thought this material is useful to present in the webinar. So when we talk about the laser ablation, what is the nature of the process? It is basically to focus a laser beam on a surface and remove material. So once you focus this laser beam on the surface, there will be a high temperature gradient and a high mechanical stress, and a plasma is formed, which creates a shock wave, and the shock wave would cause a mechanical breakdown of the surface. So both continuous wave lasers and pulse lasers can be used for laser ablation, but in this case we mostly talk about pulse lasers because pulse lasers have various different parameters that can be controlled, like pulse width, repetition rate, energy per pulse, and so on. But in case of the CW lasers, it's only the wavelength and the power that you can control. So we see here, this is from a paper by Malaysian authors on applications of laser cleaning or laser ablation coating removal from car surfaces. So these are, let me activate the pointer options, the laser pointer. So you'll see here that there is this car paint, which is mainly made of resins, pigments, solvents, and additives. And this is on a metal substrate. So once the laser beam shines on it, it develops this plasma shock wave, basically is created because the coating absorbs the radiation. And then it develops some crack network, and then it gets basically explodes, and the coating is removed. So this is a basic mechanism of laser ablation or laser cleaning. And in this case, there may be other cases where the energy is not so high to create a plasma, so there will be only evaporation of the coating. Now, I need to emphasize that in this particular case, the coating itself absorbs the radiation, but there may be other cases where the coating is transparent, and in that case, the radiation passes through the coating and is absorbed by the metal substrate underneath. And then this plasma is generated and explodes to remove the coating from the surface. And that's a different process called spallation. That's a different type of basically coating removal. But in this case, the coating itself absorbs the radiation. So let's look at some different types of lasers that are used in laser ablation. We have solid state lasers, and we also have gas lasers. So from left to right, you have the excimer laser, which is more like a lab laser. It has a UV wavelength, nanosecond pulse, and it's usually used for germicidal applications, photodissociation. So it's a very low rep rate laser, but it could be useful in some cases. Then we have another gas laser, the CO2 laser at 10 micron, which is quite popular in the industry, also for laser cleaning and also for cutting purposes. And that's a 10.6 micron, a nanosecond pulse. Then we also have the near IR laser, neodymium YAG laser with a nanosecond pulse. This is a crystal laser that can be used for laser cleaning. It can be coupled into a fiber optic, which is a big advantage. And you can also get the multiple of the wavelengths, 532 and 266 nanometers, by putting a harmonic crystal in front of the beam. And then finally, we have the Ti-Sapphire laser, which is a tunable near IR laser from 650 to 1100 nanometers. This is also a crystal laser, and it usually comes in femtosecond pulses, which is useful if you don't want the heating effect to be pronounced. But the most popular laser in our view is the fiber laser, which basically is very popular in the industry right now for cleaning. And in that case, instead of having a cavity and mirrors, there is a scribing inside the fiber. So that acts as a diffraction grating, which would reflect only one particular wavelength. So you would pump the fiber with diode laser, and the radiation moves back and forth between these scribings and gets amplified and comes out of the fiber. So the medium of the basically core of the fiber could be ytterbium, erbium, or thulium, and the amplification takes place inside the fiber. The great flexibility of the fiber laser is that, or rather the great advantage of the fiber laser is its flexibility, because you could move it around. You don't need a set of mirrors like the CO2 laser to direct the beam. So if you need to steer the beam, you can just move the fiber. It's quite flexible. It has other advantages such as high pulse energy, high average power, good beam quality, and variable pulse length. So as I said, laser cleaning is a subset of laser ablation. I keep on going back and forth to the more general case of laser ablation and the more specific case of laser cleaning. So here we are back to laser cleaning. and this would remove unwanted layers or contaminations from a solid substrate. So in order to understand what's going on, let's watch a video first. So, and this shows our 100-watt system. So you can see this is the 100-watt system, with the box being the where the pumping takes place, fiber optic cable, and then there is a laser head which has the galvos and a lens. So I'll just run this video. There you can see the plasma is glowing, and also that the vacuum pump is removing all the debris on the spot. So it's a dry process, basically. There's no contamination to the environment. This is rust cleaning of a pipe. Okay, so all right, so let's move on. So there are many applications of laser cleaning technology, and basically you have, for example, conservation and restoration. We did clean the Parliament building in Ottawa, and also bridges in Quebec. Some of the bridges were cleaned by laser cleaner. In aerospace industry, we have cleaning aircraft equipment. I'll show you some videos of the Canada Aviation Museum and ship's body parts. We did a case study for Irving Shipyard where we cleaned the plenum and the bilge of the ship. And also in industrial processes, we did go to different industries. So one industry that was making caterpillars, and also nuclear plants or radioactive decontamination facilities, we have done some cleaning. So there are many different applications of laser cleaning. So what are the important parameters for laser cleaning? First of all is the wavelength, because one has to consider that some wavelengths are heavily absorbed by some materials and some other wavelengths are not. So for example, in case of near IR, it is absorbed well by metals, but mid IR is reflected from metals. But paint, on the other hand, absorbs mid IR and reflects near IR. So one can look at, for example, if you want to remove paint from a metal surface, it may be a good idea to use a near mid-IR laser, because the substrate would not get damaged. The wavelength is reflected by the substrate, but the actual paint is absorbing the mid-IR. However, the disadvantage of that is that mid-IR is not basically is not coupled to the fiber optic, so it doesn't have the flexibility. And besides, you can also tune parameters for the near IR so that it would be not damaging the substrate. Then you have the pulse width, which basically determines how deep it goes, the beam goes into the material. So if you have big pulse width, it goes deeper, it's larger penetration depth, and smaller pulse width would not go in as much. Pulse energy, of course, would higher pulse energy means higher rate of ablation. Beam shape comes into picture. If you are cleaning surface with a lot of nooks and crannies and fine details, you would like to use a finer beam, or maybe if it's porous like concrete, you would like to use a finer beam. But if you're cleaning a flat surface, you can adjust the beam so that it's maybe 20 centimeter long as a line, and then you can work faster. A repetition rate, higher repetition rate of the laser will increase the depth of ablation at the same energy of the pulse if you increase the repetition rate, you could reduce the threshold fluence because there will be heat accumulation. And then there are also other important parameters for laser cleaning, which I took out of some papers. One of them is depth of removal decreases with an increase in scan speed. And here's a paper that shows a graph that the scan speed, as it increases, the depth of a crater would decrease. And that's simply because the dwell time of the beam on the surface decreases. Number of passes would increase the ablation rate. And here is also the effect of temperature. This is from a paper by Shamsu Joha regarding paint on stainless steel surfaces. And what is interesting is you see that once the fluence is below 3 joules per centimeter square, the temperatures stay below the melting point of steel. So melting point of steel is about 1500 C, which is about nearly 1800 Kelvin. The scale is in Kelvin. So it stays below that. As soon as the fluence increases to 3 joules or higher, there's a sharp rise in temperature and there's melting. So these three are all above the melting point of steel. And so for this reason, it's important to control the fluence. And it's also important to measure the temperature. We have been working on some sensors that we want to utilize to measure the temperature on the spot to make sure that the substrate doesn't get damaged. And then we have the competing methods for cleaning surfaces. So for example, you have the mechanical abrasive from left to right, the rotating disc. This could potentially damage the surface and cause scratches. The chemical method, where you apply a chemical and then wait for a few minutes and then scratch the surface. So this could also potentially damage the surface and also contaminate the surface. And then you have all these other methods. They're based on a secondary medium coming out of a high pressure nozzle. So dry ice, sandblasting, and water jetting. Some of them are very popular in the industry, especially sandblasting. But the problem with these methods is that all the garbage and all the contamination would go into the environment. So you need to prepare the area, and then after that, you need to clean up. And if you don't, like all the debris and all the garbage would go into the environment and create problems. So that is a point of disadvantage for all of these methods. And plus, the workers also need heavy personal protection equipment, because in case of nozzle devices, the material could bounce back and hit them. So you need to put a lot of pressure to hold the gun there and basically do the cleaning. However, for the laser cleaning, it's a dry process, and it doesn't require any secondary medium. Only light is hitting the surface. So it has basically very low environmental impact, and all the dry debris are collected on the spot by the vacuum pump. And other greater advantage of laser cleaning is its selectivity, because you can adjust the pulse energy and other parameters such as width, fluence, and so on to basically remove some kind of paint, but not the other. And I will show you a video of this Coke Zero can here, and that will become more clear. Plus, you have localized action, versatility, and controlled removal. So let's look at this video together so we understand what selectivity means. So here you see a Coke Zero can is being illuminated by the laser. It's actually our laser. And although the laser beam is shining on all the different colors of the paint, the red, the white, and the black, it's only removing the black and not the red and the white. And this is something that could be only done with laser cleaning. You cannot do this with sandblasting, for example, because sandblasting would remove everything. The reason is that we have tuned the parameters and the fluence in such a way that it is above the threshold energy for the black paint, which absorbs more than red and white, and below the threshold energy for white and red. So for this reason, it's removing black, it's not removing the white and red. So a question could arise here that is it possible to tune it so that it could remove red and not remove black? And the answer to that is no, because once you tune it so it could remove red, it's already surpassed the threshold energy of the black. So this is an interesting feature of laser cleaning, the selectivity. All right. So what are the disadvantages of laser cleaning? Because no technique is perfect. So always there are advantages and disadvantages. So one disadvantage is the need for focusing. So if you remember when I showed you the system, the 100-watt system, this lens is over here, and this has a particular focal length. So you need to keep the lens at that focal length from the surface that you're cleaning. So it's not like sandblasting where you could bring the nozzle at any distance. This has to be at that particular distance. And we also have 3 lenses here, so at different focal lengths, depending on how far you want to be from the target. So that's one requirement. And once you are at that distance, you hear maximum sound and maximum light. So you know you are at the full focus. So this is one. And then also if you compare the speed, if you only consider the time of cleaning, for example, sandblasting is faster than laser cleaning. But in the case of sandblasting, as I said, you need to prepare the environment before and also after, clean up after. So you take those times into account, then speeds are comparable. So in order to address these disadvantages, we have designed certain accessories that would make life easier. So for example, here we have the fume extractor nozzle. So you can see there are wheels on one end, and then there's an opening on the other end where you can put your laser head inside. And there's also this vacuum tube that could be attached. So once you roll the wheel on a surface, this would keep the laser cleaner at the focal distance. So you don't have to worry about maintaining the focal distance, and we'll start cleaning. We also have robotics, because robotics basically will keep the focal distance automatically, and then the factor of fatigue for the operator is also is not a factor anymore. I'll show you a video of that. Here on the right one, you can see one of our engineers is carrying the vacuum pump on his back and is holding the laser head, and also has the fume extractor nozzle. So it's like a portable unit. So let's look at the let's look at the video for the robotics. So you can see that it's the robot is holding the 100-watt laser head and is moving around and cleaning the rust on the pipe. And this vacuum pump is collecting the debris. So it's all automated. And this is very useful in the industry, especially if you want to go to a radioactive environment where you don't want to be in the place. The robot could do the job for you. So that will be one of our case studies. I'll show you a video of that later. Okay, so let's move on. There are more videos here, sandblasting and laser cleaning of ship. So let's look at that. Sandblasting first. So you can see the operator is wearing heavy protection equipment, personal protection equipment, and also all the debris is going into the environment. So now we do a similar with laser cleaning. So the vacuum pump is removing, this tube is removing all the debris, and it's a dry process, and it's done very neatly. Okay. So now I'd just like to explain a little bit of the physics of the laser ablation and dependence on laser ablation on material properties and laser parameters. So what are the important properties? Optical attenuation coefficient, alpha, thermal diffusivity, millimeter square per second, and heat of vaporization in joules per gram. And the laser parameters of importance are type of laser, which determines the wavelength, the pulse width, the fluence, which is energy per unit area, and the beam size. So I would like to bring your attention to this diagram. So you see this beam of laser beam is shining on this block and is penetrating through the block by this amount, by this depth of L alpha. Okay, so if the pulse width of the laser is too short, so it is below 10 picosecond, the thermal penetration will be the same as the optical penetration. But if the pulse width is greater than 10 picosecond, the thermal penetration depth L tau would be larger than L alpha, the optical penetration depth. Okay, L alpha is just 1 over absorption coefficient, but L tau is the square root of the thermal diffusivity multiplied by the basically the pulse width. So you can see there is a dependence on pulse width. The larger is the pulse width, the larger will be the thermal penetration depth. So now we define the threshold fluence, which is enough energy to start ablating the material. So this is energy per unit area. For short pulses, the threshold energy is given by this equation, which is a product of the density, the heat of vaporization, and the optical penetration depth, L alpha, and is completely independent of the pulse width. However, for the greater than 10 picosecond pulses, this is given by rho HV L tau, which is the thermal penetration depth, and then there will be a dependence on the pulse width. So the threshold fluence increases with increasing pulse duration. So you can see that things change at higher pulses. Here we go back again to laser ablation and do a comparison of drilling with short pulse and long pulse. So basically we have 3 regimes, femtosecond, picosecond, and nanosecond. For short pulses in the femtosecond, the drilling is very neat. You can see there is no melt zone, there is no micro cracks, no shock wave, no heat transfer to surrounding areas, and just basically the solid is being vaporized. But if you go to the longer pulses, all kinds of liquid physics effects will take place. So you will see the shock wave, the micro cracks, damage caused by adjacent structure, surface debris, ejected molten material. All of this will come into picture, which is representative of liquid physics. So if you want the heat effects to be less, it's better to use the short pulses. So my point is not to say that we shouldn't use long pulses, because all of our lasers are nanosecond pulses. They have nanosecond pulses, but I'm just trying to communicate that for larger pulses, the heat effect is more pronounced. Here is the comparison of 3 holes basically made by 3 lasers, femtosecond, picosecond, and nanosecond. And you can see the femtosecond is quite neat and sharp, but in case of the other two, there are all kinds of debris and molten material around the hole. Also, let's look at the long and short wavelength behavior. We talked about this a little bit before, but you can see for metals, at longer wavelength, the absorption coefficients, for example, 10 micron for CO2 laser is very small, but as you go to the shorter wavelength, say at 1 micron, the aluminum starts rising. The absorption coefficient of aluminum for the near IR becomes greater. But in case of ceramic, glass, plastics, and paints, it's the opposite. At higher wavelengths, at 10 micron, they have large absorption coefficient, and at smaller wavelengths, it decreases. So they behave differently. So for this reason, if you use a mid-IR laser like a CO2 laser, it will be inherently safe when you want to remove paint from a metal surface. But you can also do the same if you pay close attention to the parameters of the laser. And our engineers actually have some recipes with our laser systems that are suitable so that you can use the advantages of fiber optic, which cannot be done with the mid-IR lasers. So you use the correct recipe, you would remove the paint or rust efficiently, and you won't damage the substrate. Here's also a comparison of Galvo and Polygon scanners. So normally the lasers, they have Galvo scanners with two mirrors. One of them is rotating, one is stationary, and this is how it works for lower power lasers, including our 100-watt laser. But when you want to increase the power of the laser, these galvos, they become heavier and heavier and slow down. So you cannot scan as fast. So in order to overcome this drawback, the Polygon scanner has been used, which you can see over here. It has multi-facets and it rotates very fast. And basically, you know, we will shine the light. It will scan the light. So you can also couple these Polygon scanners with CW lasers. It's possible to have a combination of CW lasers, which are more available and they're not as expensive, with a Polygon scanner. And they have certain advantages, including being faster. They could tolerate higher power levels, and basically they could be coupled to CW lasers, and affluent removal is also easier to remove due to fast scanning speeds. All right, so we talked about the theory quite a bit. Now let's go into some applications. So now we start the part of applications and also case studies. So as I said, applications is just something that I've dug out of the literature or different technical journals to show you, and the case studies are those that we've done ourselves. So here you can see the aircraft is in a hangar and the robots are cleaning different parts of it. So one question is, why do you need to remove the paint for the aircraft? Well, first of all, the quality of the paint is better. The new paint quality will be better if you remove the old paint. And secondly, you don't want to add weight to the aircraft. So in this case, you can see the robots are probably using a CO2 laser. They're cleaning different parts of the aircraft, and one can also do the same operation with near IR lasers and have the flexibility of fibers to remove the debris. Another very interesting application is laser cleaning for nuclear decontamination. So in Canada, for example, in provinces of Quebec and Ontario, we don't use coal at all. So Ontario uses 60% of its, or makes 60% of its electricity through nuclear generation, power generation. And Quebec has a lot of water. So 94% of the energy is from hydroelectric. So in case of nuclear power plants, they are a good replacement for coal, but the problem is that every 30 to 40 years, some cracks develop in the structure and they need to be decommissioned. So one has to get rid of all the concrete of the walls, which are contaminated, radioactively contaminated. So you can't just throw them out. And there are also tools, metal tools inside their reactor that needs to be cleaned because they are radioactive. So what happens is that the corrosion of metal pipes will go into the coolant, the reactor coolant, and that will recirculate and go into the active area, gets radioactive, and comes back and deposits on the pipes in the form of oxides. So cobalt 60 deposits on feeder pipes. It has a half-life of 7 years. So these tools need to be cleaned. So laser cleaner is a good way of removing these oxides. And also the cleaner, the laser radiation goes through the oxide. They're transparent. And the metal gets hot and then the plasma is formed. The shock waves removes these oxides. So it's mostly a spallation process. It's not like the car paint. It uses the spallation process because the oxides are transparent. So let's introduce some of our laser systems so that you have more familiarity with what we have produced. So we have a number of different systems of different power levels. So this is a 100-watt system that we originally built a few years ago. This was our first system, and you can see the fiber optic, the galvo, the lens, and it has various repetition rates, pulse width. There's also an iPad on the top where you can use different recipes that has already been recorded and adjust all the parameters. We also developed a 200-watt system a few years ago. This one has some cabinets. Obviously, it has twice the power, but it also has some cabinets that could store basically lenses, different lens accessories, and also goggles. You can place them here. And it has a narrow form factor. So that's the 200. Again, it has a variable tunable rep rate and pulse width, and the fiber length is 8 meters. In case of the 100-watt, it was only 5 meters. Then there was a need to have a smaller dimension laser cleaner, and that's why we came up with the idea of the 100-watt Gen, we call it. So it's like a suitcase that you can pick up. One man could pick it up, and it has, instead of the iPad, we have another user-friendly interface. It's called a touch coder, and the laser head is also smaller. So this is very useful, especially in ship industries, because sometimes the worker needs to carry these laser through the hatches, and there's not enough space for a large system to go through. So they would like somebody to just carry it like a suitcase. So this is also ready. Here are some features of the laser head. You have an air line to clean the surface. You can blow some air there. There's laser safety signals and some interlock switches, button switches in case something happens. You could shut off the radiation. And there's also an idea that in this case the laser beam is perpendicular to the body of the laser head. You can also have another design where it acts like a flashlight. So the beam and the body are parallel. So maybe for some applications, this will be easier to get into tight spaces. We just recently developed the 300-watt laser. You can see the two views here. Although it's not 100% ready, it should be ready by end of June, I suppose. These are some of the specs of this laser. that are seen in this table. And also we have the 500-watt system that has been made and has been purchased by several organizations and companies. This is our highest power laser, 500-watt, 1064 nanometer. And you can see you could coil the fiber optic on top of this and put a lid on it to protect it. It has 11-meter or 22-meter beam delivery fiber cable, and it has a chiller because you need to cool it. Separate water cooling system for laser engine, optics, and laser head. And these are some of the features. You can also lift it. You can see there are some lifting hooks on its side. Here you can see the picture of the chiller for this laser. 15-meter main power cord to the chiller system, leak-free, quick disconnects, keyed color codes. So these are all the features of the 500-watt system. So now we can talk about some of our case studies. So the first case study that was done back in 2017 was going to the Perma-Fix nuclear or radioactive decontamination facility that deals with low-level and medium-level radioactive waste. They process and clean different objects that have been radioactively contaminated. And there we had basically our system was brought there, and they defined a negative pressure area where they routed the fiber optic and the laser head into the negative pressure area, whereas the box, the engine of the system was outside, was kept outside of the negative pressure. And here you can see engineers are working to clean different radioactive objects. The metal plate here, here's a disc, and the laser head is been wrapped in plastic so it doesn't get contaminated. So there's a small video here that I would like to show quickly. Maybe I won't show all of it because we'll send you this, but I'll show part of it. So you will see that the radiation engineer would measure the radiation of the object before the laser cleaning and then after several passes. And some of the objects, they required more passes to be cleaned. The level of cleanliness was defined as 1000 dpm. And for example, for concrete, you needed 4 passes to remove this contamination. So let's look at this for a few minutes. So 101 system. This is the metal plate that is being cleaned. This large vacuum pump basically removes all the debris. I'll fast forward this. Here you can see a C clamp is being cleaned. It took a few passes to, after 2 passes, initially it was 5,000, and then after 2 passes, its radiation level was brought to 1,000. Here, the body of a C clamp is being cleaned. It took 2 passes to bring to less than 1,000. And over here, there is a torch, and this is a concrete block. So you can see in this case, the beam is smaller so that it could penetrate through the pores of the concrete. So this was our first case study. And the second case study was is a relatively recent one, radioactive robotic laser cleaning at McMaster University practice. So move this out of the way. Yeah, so particle accelerator decontamination facility. So McMaster University in Hamilton has Hamilton, Ontario has a hot cell facility. So we made an arrangement to take our laser cleaner with a robot, and they would provide us with the F-18, which is a radioactive material they can make over there. And this radioactive material, F-18, has a very short half-life of 109 minutes. So the purpose was that if in case there is some error and a mess is created, you just have to wait for 24 hours for all of the radiation to decay. So there won't be any issues. So this was created and was put in a solution, and therefore I think a methanol solution, and it was applied to different metal surfaces by a paintbrush. So here you can see there are 5 different type of metals were used. Some of them were soft and some of them were hard. So we have brass, steel, stainless steel, aluminum, chrome, vanadium. And the laser head is being held by the cobot. This is one of our cobots. Of course, we had to make some adjustments for the height so that the metal is inside the hot cell. It's located here, and then automatically it was scanning and cleaning these. So the initial levels varied between 5,000 to 10,000. So we defined the level of 500 counts per minute as the clean. So we did several passes and made measurements till we got to that 500 CPM level. So for some of the hard substrates, we use a 350 nanosecond basically pulse width, and for some others we used, or which is softer metals like aluminum, we used 200 nanosecond. Also, we used different rep rates. So the result of this cleaning was presented in the WM 2022 in Phoenix, Arizona as a poster. And here I'll show you, this is the table for different, you can take a look at the table about the parameters that were used and also how many passes were used. So mostly 350, but for aluminum, 200 nanosecond was used. So we were able to bring down the contamination level below 500 in all cases. So let's take a look at the video here. I'll give you an idea of what was going on there. So I'm just going to remove the laser pointer and activate this YouTube video. So this is inside the hot cell, and this is the table that carries the cobot. The cobot is holding the laser head. So you will see in the video that at the beginning, the engineer would measure the radiation from the contaminated metal. This is the brass that is being cleaned. And then the laser comes and cleans it. And after cleaning, they again measure the amount of radiation. So let's take a look. So here he's measuring the amount of radiation before the cleaning with the Ludlum detector. And it was typically 5,000 to 10,000. So he would take a few readings and average them. And then I'll fast forward to 7, where you can see the laser cleaner. Let me start from here a little bit so that you can see. Starts and robotically controlled starts to clean. So it does several scans. So after doing these scans, then we go to fast forward to point 12, where they measure the radiation after. And if the radiation was below 500, then we stop the process. So that gives you an idea of this radioactive decontamination. Okay, so another case study was done at the shipyard. Basically, Irving Shipyard trials at Halifax Shipyard and Shelburne Ship Repair. So all of our lasers, 100 watt, 200 watt, and 500 watt, was taken there to basically clean the plenum and bilge of a ship, and also some work that was done onshore to clean some metal pieces. So here you can see the ship is wrapped in a tarp because they were preparing to clean that with sandblasting. So they needed to isolate that. So, and these are some onshore green tent where some cleaning was done. These are all the boxes of our laser products. The first operation was done with the 500 watt laser. This operation shows the 500 watt laser is outside on the deck, and then there was a 15-meter fiber cable that was routed through and cleaned some paint. And also they wanted us to make a 4 mil average profile on the surface. So we were able to do that. Not only clean the existing paint, but also make a 4 mil average profile. Then they wanted to clean some areas in the bilge, which meant that you needed to lower the laser to that through the hatches to the bilge. And the only laser that fit the profile, it could go through the hatches, was the 100 watt. So for this reason, the Gen version would have been more suitable, but at that time it was not ready. So there were some space constraints there, and rust and paint were removed. Then the 200 watt laser was also used in the Halifax shipyard onshore. You could remove rust from 6-inch pipe, bike frame, welded plates, and so on. And here is in Shelburne, which is another area, another city, basically. So rust on flat surface of a steel substrate, heavy corrosion over steel substrate, rust on steel substrate, and intersleek paint over steel substrate. So all of these were cleaned successfully, but at the end, we got some feedback from the managers of Irving that they would like the reduction of size of laser head, reduction of size of laser controller, extending the fiber optic cord, and actually coming up with faster and better recipes. So some modifications are required before Navy could use this. Some other case studies, I'm not going through all the videos. I'll send you these videos. Here is removal of leaded paint that basically we have to use also a BOFA filter, not only a HEPA filter, but a BOFA filter that has all these, you can say, compartments with filter scrolls, plates. So the heavy contaminants, heavy particles, they go on the outside by centripetal force, and they drop off in these scroll plate areas. And then the rest of the air, which has smaller particles, will go through the HEPA filter. So one has to be more careful with lead, obviously, because it's toxic. And then here we have another case study testing at Canadian Aviation Museum in Ottawa, where engine parts were cleaned. There is rust and soot on these engine parts that were cleaned. You can watch the video when we'll send you the link. Here is another case of polygon scanner. You see the polygon scanner is over here, is rotating really fast. Let me see if I can show a few minutes of this. So here's the polygon scanner. So in this case, this is just the demo model of a polygon scanner. So you will see there are 8 lines because the facets, they have different angles, and the camera is not fast enough to distinguish between, each one is, it's some kind of optical illusion. They're not all simultaneously illuminated. There's one and then there's the other, but because it's so fast movement, you see 8 lines. So we have been using polygon scanners recently, a more sophisticated model, and that has all the facets aligned so that there's only one line. So that's the polygon scanner case. And then we also have another method that's called the non-destructive testing that we have been using recently. Uses a capacitive 2D imaging method and impedance spectroscopy to find where are the locations of rust on the surface and also in the body of the surface. So as you can see here, 2 electrodes are placed on the object, and this creates a capacitor. If there is rust anywhere along the way, that will show as dark spots or white spots. If it is on the surface, it's white spot, and if it is at the body of the ship, it's dark spot. So we have been using this to identify the location of rust. And finally, as our last case study, this is again, sorry, this is not a case study, but this is an application again. So we haven't done it, but the information is available in this webinar. In case of food industry, you need to clean these greasy plates, barbecue plates. So the coating absorbs near IR very well, and basically, could remove them by creation of the plasma and the shock waves. So these sticky biofilms could be removed very effectively. And in case of bacteria removal, also this paper talks about 2 different types of lasers, the neodymium YAG laser and also CO2 could remove these sticky biofilms that are hard to remove with detergents. So they were quite effective in removing the bacteria. So we come to the end, and let's do a conclusion. So what we showed here, laser cleaning is more environmentally friendly, reduces damage to substrate. It has a great selectivity by tuning the parameters, does not require secondary medium, reduces health hazards to the operator, is less noisy and more economical as compared to other methods such as sandblasting, water jetting, and so on. We looked at the pulse duration issue, and different parameters, fluence, repetition rate, wavelength, how do they affect the performance of laser cleaning. We compared polygon scanners and galvo scanners, and we also compared CO2 laser, mid-IR wavelength with near-IR laser, the pros and cons of each one. So we came up to a conclusion that laser cleaning could be a very good replacement for sandblasting in shipping industry, because it's really a mess when you use a sandblaster in the shipping industry. It really damages the marine environment. So that's a really good method to replace it, and the Navy is really taking it seriously. And finally, we showed a robotic laser cleaning of a radioactive F-18 isotope from surfaces of many different types of metals. And we did present this work in the WM 2022 conference in Phoenix, Arizona. So with this, we come to the end of the webinar. I would like to thank you for listening. And there is also a webinar feedback form that will be sent to you. If you please fill it out. If you have any comments or suggestions as how to improve the webinar or add anything you wanted to be seen that you didn't see, please let me know. And at this point, I would ask the audience if they have any questions, please either type or you can unmute yourself and ask me. Are there any questions? I would also send you my email here one more time. If you think of a question later, you want to have more information about any particular laser and any of the case studies, especially if you watch the video later, you could email me and we could discuss. So if there are no more questions, once again, I thank you for the attention. And here's me, by the way. Hi. So I hope you have a good afternoon and stay safe. We'll have another laser cleaning webinar in 3 months again, so with more case studies. Thank you and have a good day. Bye.
Thank you, Rez. I'll send you some questions. Thank you.
Thank you. Bye.